heard it right, and let me introduce you to high performance modeling in Python. To do that, I think we first have to talk about the big F. Fortran, still the king of modeling, high performance modeling of almost any kind. And I'm sure most of you know Fortran a lot better than me, so I don't need to tell you what the strengths and weaknesses of Fortran are. Well, maybe you need to get reminded of some of the weaknesses, because the more experience you have with an ecosystem, the more experience you also get to working around the problems that it might have. So here's our perspective and our motivation why we would like to transition away from Fortran or just try something different and see what happens. And this is what we call higher level geophysical models, since they are in a higher level programming language like Julia or Python. So we thought a lot about this, and I think there's some decisive advantages. We don't have to go through all of them. One that we're going to focus in this talk a lot is that you can take the same code and run on GPU, since in Python everything is dynamic. So in the background you can switch out things without the user noticing, and you can actually throw your CPU code on GPUs with very little effort. And yeah, but I actually want to highlight this reason is because, well, why I built this, why we built this is because I liked it and because I don't like writing Fortran, and that's all the reason I needed for this. And of course, there are some advantages to writing Fortran, but we'll get back to this later, and maybe some of the advantages are not as big as you might think. So from the get-go, this sounds a bit like an insane project maybe, but yeah, we'll see how it goes. Now to add a bit more data on this, so even some of the Fortran enthusiasts are getting, well, a bit weary about some of the problems in the ecosystem, especially the tooling in Fortran is really underpowered compared to more modern languages. The lack of a package manager, the lack of GPU support, and build systems that are not really that modern anymore. Your students probably use mostly Windows PCs, and I don't know if it's possible to compile CESM on Windows, but I'm sure I would not like to try to keep my sanity. And I think a lot of the Fortran people also agree on this, and we had some really nice discussions about it. And so I think as a modeling community, we can really maybe also use this research to further how we would like to design Fortran models in the future. So I think, yeah, ultimately the message is really something where I want to bring together the community instead of dividing. So while hopefully all the problems with Fortran are getting fixed, we'll try something different. We do high performance ocean modeling in Python. And the way this works is illustrated here. So we have this Python stack, since Python has terrible performance out of the box in the native language. So you need to pull in other libraries and build on a whole library stack instead of using the core features of the language, which is a completely different paradigm from Fortran. So here we leverage both NumPy and JAX, which I named before. So JAX is a Google product for machine learning, but it turns out it's actually really good at accelerating code of any kind. It does it through this compiler XLA. So it is just in time compiled through XLA, and that can talk to GPUs. And so can the rest of our stack, which is PETSI, which we use for the barotropic solver, that we talk to with PETSI for Pi, that also works natively on GPU, and so does MPI, which we talk to with MPI for Pi and MPI for JAX, which I wrote. And out comes this ocean simulation. Here it's a snapshot of our 1 degree setup. So the product that combines all of this is called VEROS, the Versatile Ocean Simulator. It's a translation of PyOM, which is a Fortran ocean model despite the name, to Python. So we took this Fortran model and did more or less a one-to-one translation to Python, which also gives us the opportunity to test against it. So we can really make sure that we solve the same problem in both languages, and we can compare the performance in apples to apples comparisons, which is also a huge asset for us. It runs on pretty much anything from laptops to clusters and even GPU clusters. It's a full-fledged primitive equation model in Z coordinates, so it's not extremely fancy, but it still does. It's not a toy, so you still have a full realistic ocean if you want to. And yeah, about 140 variables in the model, so it's a reasonable level of complexity. This is not orders of magnitude below something that you might use in a real climate model. Just to quickly show you how we went from Fortran to Python, because I think it's often interesting for people to see this. It sounds like a daunting task, but actually it's not as bad as it sounds. So you can just, since the syntax is actually, well, you can only translate the syntax, but the logic, the semantics are actually pretty similar, which is not a coincidence because Python's array capabilities are modeled after Fortran's. So you can mostly just go on replacing syntax with regular expressions. So you have this one which replaces do loops with for loops, and then you already have a first implementation that you can almost run, and then you fix some of the points where it breaks. But the first iteration is pretty fast, and then you iterate from there. So to show you how to translate some Fortran that you might be used to more idiomatic Python. So take this very small part of a subroutine here. So this is a loop in X, Y, and Z. No, actually only in X and Y. Then in every iteration you have a conditional, and then based on the conditional, you set some values. In Python, you have to write this a bit differently because everything has to be vectorized operations. You can't write loops, or if you do, then your performance plummets. So you don't really want to avoid loops. Similar to, I don't know, if you use to MATLAB, then I think you have the same issues. So you write everything with arrays, and sometimes you have to get a bit creative, like this conditional inside the loop here. So you just assemble a Boolean mask and then multiply that in the end. But the results are the same, and this is a completely vectorized formulation. And yeah, I would say like 90% of the code, at least, you can just translate one-to-one in this manner. It's very straightforward due to the way these models are written. And you can already see that these loops are getting translated to index shifts. So instead of having an overlap here, or a loop that goes from the second element to the second from the end, since you have an overlap of 2 in this case, here we operate on these slices, which go from 2 to -2, so from the second also to the second to last. And by rewriting everything to this slice notation, which is not easier to read, I would say. If you're used to it, then it's maybe about the same, but it's definitely not better to read. But it's pretty concise, and it works fast in Python. Now we also coupled that with JAX recently, and the changes from this NumPy formulation to JAX are very, very small. All you do is just change some types and apply some decorators to your functions. And the only thing we would have to get creative about was MPI, since JAX has no MPI support. So we had to write MPI for JAX, which then registers MPI communication operations as JAX operations. And now you can just use MPI within JAX code, and it will recognize and optimize them. So far about how to build something like Veros. Right. I hope we have enough time. Let me try to show you a very quick demo of how it looks. So here's a shell. And we create a new Python environment. So this creates a new Python 3.9 environment, and now this is completely empty. So if I type Veros, then it says unknown command. So now I just type pip install Veros, and this will install Veros from scratch. So it just pulls the latest version from the repository and installs all the dependencies on this virgin Python environment. This takes a couple of seconds. Hopefully it will be done very soon. So you have to contrast this with setting up a make file and changing paths to libraries and compiling it and getting a compiler and everything. So this is just all there is to it. And now we have the varus command, and we can do model runs with this. So we can do a varus copy setup, like a 4-degree setup. And then this is our setup file where we set all the settings of the model, like the domain and the time stepping, but also the diffusivities and viscosities and different advection schemes and whatnot that we can switch on and off. And then to run it, we just do varus run and this file, and then it will execute the setup. In this case, yeah, it's a 4-degree global setup. The first run takes a bit longer since it has to initialize some paths and fill some caches, but yes, I think if we wait a couple of seconds. Oh yeah, now it's running. This is just NumPy on CPU. We could also use JAX or use GPUs. In this case, it's just running on my laptop, so I don't have any GPUs here, so I can show you that. You can also use multiple CPUs. You can run it on a cluster, multiple nodes. It's all completely parallelized with MPI. And here's running, and the simulation is done because it did 0 time steps. And that's it. And it wrote the output in .cdf, in this case, just the initial conditions. And we could also do something like this, and then do, I don't know, device GPU and backend JAX or so. And if I had any GPUs, then this would just run it on GPU with JAX. And I can even run it on multiple GPUs. If I do something like this, put MPI run in front of this. In this case, it would run on 2 GPUs. So most of this is like we're used to, only that the process, I think, is a bit more streamlined than in traditional models. All right, let's get back to the presentation, if I can find it. Sorry, I think I have to end the screen sharing here. Oh, here we go. All right. So that was the quick demo on how to use varus to show you that it might have some tangible advantages to use varus. Now imagine giving this to your students and saying, I don't know, in a workshop setting, and you just change some settings and see what happens. So it's like, I think, really easy to get into and to have the first steps of success and hopefully excite them for the field. So this is an overview, just how we do this, high performance computing in Python. So I think it's quite simple to write. Once you get used to these index shifts, then it's pretty much the same as you would write a Fortran model. It scales well since we can use MPI. And as I just showed you, it runs on any hardware, so we can just switch a flag and then it uses a GPU instead of CPU and runs multiple devices. And so the only thing left to check, how fast is it? How does it compare to Fortran? So this is a slide that I showed at AGU last year. We'll get a bit into that. Just let me summarize the main takeaways here. So we are close to Fortran, really close to Fortran actually with JAX. So this is the number of processes on x-axis and the runtime on the y-axis. And if I go to something like 256 processes for a 1-degree model, then it's indistinguishable from Fortran, JAX and Fortran. And for few processes, it's also indistinguishable. And only for an intermediate number of processes, we have like a 20% or so gap between the two, which I think is acceptable and probably amortized by the time you save setting up your environment. So we almost match Fortran in most situations. And but I think the really exciting thing is how it scales on GPUs. So this is really, really expensive GPUs, and 16 of them. These are NVIDIA A100s, pretty much the most expensive GPU you can buy. But it turns out you can use 16 of them at the same time. And if your problem is big enough, like in this graph, then you get almost perfect linear scaling with adding more GPUs. And out comes this, which is a 0.1 degree model, which we do on a single GPU node with 16 of these GPUs. So instead of having a whole cluster of thousands of CPUs, I've seen people run this on 2,000 and 4,000 CPUs. we just use this one node with 16 GPUs to integrate this 0.1 degree model, and we get like 1 year per day, 1 model year per day, which is also comparable to these 2,000 to 4,000 CPU core runs. And we can't measure the energy consumption in this case, but we could measure it in simpler cases. And there we found like a factor of 3 or so between GPU and CPU. And in this case, it should be even higher, since this is very much an ideal case for GPU. So I wouldn't be surprised it would be like a factor of 10 more energy efficient than a CPU run. So this is, to us, this was really exciting to see how well GPUs play with Earth system modeling and with Python and whereas in this case. And all of this is through JAX, so there's no, we didn't handwrite any GPU code. This is just JAX taking our Python code and putting it on GPU. Now here the results a bit bigger, but I think we might be running out of time. So if you want to look at these, just read the paper. These graphs are just literally taken from the paper, and we have a lot more discussion on this. Oh, there's a raised hand.
I can wait to the end. That's okay. You can go ahead.
Okay, let's take the last few slides, and then happy to discuss this. Yeah, and here's a summary again. So we use 16 of these GPUs. They have combined about 600 gigs of memory, which is just enough for this setup. And we can even, so with Python, we can also switch between single and double precision just with a runtime flag. No recompilation or anything necessary. So we can also do this in single precision, which we did. And so this is actually done in single precision. And to conclude, I wanted to go into some of the open problems that we see and the next steps. So one thing, this is not really, it's not pretty to the eye, but luckily Python also gives you the possibilities to put in your own abstractions. Since you can, Python code is so dynamic, so you can pretty much do anything you want in the background. So we really have this dream of this unified API for writing models in a very clean and concise way that separates physics from numerics. So instead of doing all these index shifts and finite difference operations, we would do something like just say, interpolate this to the T-grid and then multiply these quantities, and it figures out what to do automatically. So this is really something we envision for the future. So to really unify this vision of good usability, performance, and also good maintainability and ability to modify the code, which is what we're lacking at the moment, and which is a bit easier, arguably, in Fortran, since the community standards are so well established. And just some quick last slides. What else can we do with it? Well, there's one interesting thing, that JAX code is also natively differentiable. So JAX gives you tools to compute gradients of arbitrary functions that are written in JAX. And we kind of got this by accident. We didn't pick JAX because of this. We picked it because of the performance that was really good. But we also get this as a cherry on top. And this really opens up some very exciting opportunities that also other people I think are quite excited about. So we can evaluate here the equation of state, for example, for 3 at one point of salts and temperature and pressure and get a value. We can also ask for the gradient at this point just by doing JAX grad and applying it to this function. And this opens up a lot of synergy with machine learning, since you then can train your physical model, which in this pipeline. So here we have some inputs, and this is like a machine learning model, and this is a physical model. And if your physical model is differentiable, then you can train this end-to-end with backpropagation. There's a lot of technical difficulties to this, and this is still experimental, but in theory, and people are already doing this, this should open up a lot more potent synergistic hybrid models with machine learning components that I think is definitely exciting to experiment with. In a similar way, so some people are using this for emulation, so to abstract away the whole model, like in this paper, and then they have an 80 times speed up or so. And this is end-to-end trained with a physical solver that is very simple, like a shallow water model. But now we can drop in our whole GCM and see what happens. Really, I think for the first time in in history, at least with this fancy autodiff schemes. And similar things are done for subgrid scale parameterizations. And yeah, to close, I think the synergy with machine learning is really exciting also to me, because there are so many things that we don't understand as humans about GCMs. And I think machine learning has a good promise to actually help with these questions, like finding causes of events, or figuring out information propagation, or searching for different steady states or tipping points or so. So things that have been traditionally very hard to tackle might be easier with machine learning. At least I think it's very exciting to try, and with Veros, I think we have a very good tool at our hands to do this. And yeah, that was it for me. So if you want to know more about this, we have a paper that just came out last month in James, and otherwise, feel free to hit me up here or on Twitter or email, whatever. Thank you very much.
Great, thanks, Dion. Really fascinating stuff. Gokhan had his hand up first.
Yeah, I had two hopefully quick questions. One was the CPU GPU comparison that you showed. Was the CPU part using identical bandwidth as the GPU part? Because traditionally, if you compare it with the old CPUs, the bandwidth is so small that it doesn't provide a fair comparison at all. And that's what.
You mean network bandwidth or memory bandwidth?
Memory bandwidth. That's the key.
Right.
So if you are using the old CPU architectures with the low bandwidth, then of course CPU is going to come down.
Well, GPUs have naturally much higher bandwidth, but that's right, also one strength of the architecture, isn't it?
Right, but the new CPUs that are coming out have identical bandwidths as the GPUs now. So that would be probably a better comparison. You need to probably scale your comparison taking into account the bandwidth with the GPUs and CPUs. The second question that I was going to ask, that's quite nice actually, Python and converting to a different code base. When you showed the examples, you always had hard-coded 2s and -2s. But if the overlapping regions are only 1 or 3 or 4 elements, do they need to be changed, or can you just use variables instead of hard-coded 2s and -2s?
Oh, you can definitely use variables. So just for readability reasons, we didn't want to have it all clustered with these variables. We used hard-coded values, but there's nothing that stops you from using variables. Or I talked about abstractions, like dropping in your own array types that are already aware of what their overlap is, and maybe do stuff like automatic triggers automatic communications when you go over the overlap or so. So with more effort on this front, there's a lot that you could do, and something that we would also love to do.
Okay, thank you.
And about the bandwidth, I think it's a very relevant point, of course, since all of this is bandwidth limited. But then again, well, okay, there might be new generations of CPUs that might be able to catch up to this. But I think it's still very relevant to compare this to the things that people are using today. So
well, I mean, we can discuss it later, but what I'm told is essentially usually the CPUs use the bandwidth technology from 4 or 5 years ago, whereas GPUs use the newer technology. So the new CPUs that are coming online apparently are using the new bandwidth technology. And in that case, this difference between CPUs and GPUs may actually disappear.
Let's move on, because these guys are in Europe, may not be able to hang around till the very end of the session. So let's a couple more fairly, hopefully, concise questions. Bob?
Thank you. I enjoyed the talk, but you noted that there are some constructs that you have to really work hard, like a logical test, to make them work. You have to recast them as masks. Are there some operations that you would find in a kind of a more sophisticated ocean model that you simply don't know how to map onto this? For instance, non-local vertical remapping, where the data may depend on where the data flows may depend on the properties. So for instance, we remap in the vertical in a way that you can't necessarily predict when you've written the code. Are there workarounds or techniques that you found that work well for more elaborate logic like that?
Yeah, so we actually had this case with, so you typically have this case with something like linear algebra. So you're having an iterative solver. So, first of all, you don't know how many iterations to do. Second of all, everything depends on the previous iteration. So it gets a bit messy. So either you use something like Petsy, or you if there's nothing out of the box, one thing that we did for Veros is we hand wrote a tridiagonal solver, which is like 10 lines of C code or so. Well, that's maybe an understatement. 40 lines of C code, and you can compile this with Python while installing the Python package, and then also call that from JAX. And it's completely optional. Like if a student install this and they don't have a C compiler, then it just doesn't install it and falls back to pure Python. But if you're on a supercomputer, we really care about optimizing the last 10% or 5% or 2%, then you can handwrite some performance critical parts in C or in CUDA and then call into them seamlessly. So that works well. And I think with like a 99% Python, 1% machine code model, I think we have a really good compromise in terms of maintainability and performance.
Okay, I did see some other hands, but they seem to have gone down. And we need to move on. But I just point out that this is, to me, quite reminiscent of the very first version of POP, which was written for the connection machine, which required everything to be written in terms of array operations, no looping. So many of these same constructs existed at one time in POP, and then over time, as the cache-based architectures came along, we had to back out of that into looping structures. So it was a much more readable code 20 years ago. So I really have an appreciation for this this way of writing models. My question is the degree to which this sort of Python JAX stack is amenable to sort of hybrid language codes. And you sort of mentioned that you could write C core kernels. If suppose we wanted to implement the barotropic solver in MOM6 using this technology, is that a feasible pathway in your mind? So
you mean?
So
like
starting
XLA
with the
or
Fortran
JAX?
code and working through pieces of it, converting them to this software stack.
So you have most in Fortran and only a small part in JAX or so?
Perhaps, yeah. As opposed to writing it in ACC or OpenMPI.
I see. Yeah. Maybe. Well, it's a bit awkward to go from Fortran to Python to C++ and then back, but I guess it could be done. I think the biggest strength of it is actually if you go all the way and do all of it in it, and then just do small parts in something lower level instead of most parts low level and then some high level.
Mm-hmm.
But I talked to the people who built Fortran, which is the guy in the hat here. I think his name is Andre, and he was also quite excited about using XLA as a part of Fortran or as an Fortran compilation target. So you could use the JAX compiler from Fortran through Fortran, but it doesn't exist yet. But he was excited about the possibility of this. So if this is something that also excites some of you, then you should take it up with him. I think he's a great guy, and I think there's also some exciting possibilities here.
Okay, Santa, real quick.
Thanks, Frank. Let's see. Okay, thanks. Very quickly, are there any plans or future outlook of how these dependencies that are currently with the Python Ocean model, the PyOM version 2, how are these going to evolve? Do you guys plan to keep it that way? Or would there be some development of the original Python Ocean model version 2, or just a broad outlook of how things would evolve at your end? Thanks.
Yeah, thank you. Yeah, we're definitely open to extending the Python model and going above PyOM, or even, I mean, now we've kind of shown that the process works, and I think we captured at least all complexity that I'm aware of that is like in a real GCM like POP. So I think computationally or numerically, there's not that much fundamentally different about bigger GCMs. So we could even apply the same process to something else and then have that, now that we have proven that it works, the methodology. So we're currently collaborating with other people who want to build their own components in this paradigm. So we have someone building a sea ice model and someone building biogeochemistry. So if you have an atmospheric model, so we'd be very excited about trying it out. And then once we have all of these components in place and we can see how all of this is orchestrated, works together, also on GPUs, maybe I think that would be very exciting also to go into this direction. But obviously it's a very long way, and we're a small team, so we don't have that many resources. But if any of you would be interested in collaborating or so, then we would love to talk about it, and yeah, just reach out.
Great, thanks again, Dion.
Thank you.
Great talk. We're about 10 minutes behind, so I think we need to move along. And next up is Matt Harrison from GFDL.
Okay, thanks, Frank. Trying to share this. Okay.
Looks good. Yeah.
Okay, my mic's okay?
Yeah, sounds good.
Okay. So the title of my talk is Improved Surface Mass Balance Closure in Global MOM6 SIS2 hindcast simulations. And for this study, I'm using both the JRA 55DO forcing, which is, of course, what's used for the Core 2 protocol, and I'm also using MERA version 2 atmospheric reanalysis. And that's hourly data. And I didn't make any modifications to the MERA forcing. So this work is it's been submitted to James with my co-authors here, and it's already been through the first round of reviews. So it should hopefully be out shortly. So sort of big picture with the hydrologic cycle in a fully coupled model, water is approximately conserved. So you have phase transitions, evaporation from the ocean and lakes, for instance, transport by the atmosphere, storage in groundwater reservoirs, in snow and ice over land. But in total, that mass of water would be conserved in a realistic system. In ocean hindcasts, we have to usually resort to some ad hoc way to close the hydrologic cycle. So what we usually do is we prescribe precipitation and then either prescribe or diagnose evaporation over the ocean surface. But this will invariably lead to an imbalance between these large terms and a resulting drift in sea level. So you want to get rid of that. So what we've been doing for some time now in GFDL based hindcasts is we're diagnosing that imbalance over the ocean at each coupling time step, and then we make an adjustment to the precipitation in order to balance global net evaporation, and that has been the methodology we've used to avoid sea level drift. But the problem with this is that you're neglecting storage of water over land. For example, wintertime storage in the Arctic. And then so this is going to introduce a bias in your surface mass flux, doing this global offset. But on the other hand, we typically use virtual salt restoring to maintain sea surface salinities, which is clearly unphysical, but it's something that's been employed pretty routinely for a long time. And you also have a lot of uncertainty associated with the reanalysis precipitation. So that just might argue for the need to have these sort of artificial damping terms. So what I'm going to propose here is that if you include a land model component, then this will allow you to kind of recast the way we're closing the hydrologic cycle. So what I did is I used our land model component that's part of our fully coupled system, and that's getting forced with the reanalysis fluxes, and it's getting the same boundary conditions that we're sending to the ocean. So I'm bringing in the land, and in order to before I bring in the land, I've got to spin it up and make sure all the land reservoirs are balanced. So now, instead of just constraining the mass flux over the ocean, I'm constraining the mass flux over the ocean and the land, and that's more physically consistent. Okay, because then we can allow for land storage. So in addition to that, I'm also going to introduce a constraint on the poleward moisture transporter, or the poleward moisture transport that would be implied by the surface fluxes. So, if you take a region, for example, I've selected 40 degrees as a transition point, and that's roughly where the ocean switches from being net evaporative to net precipitation. So over the region north of 40 degrees, I can apply a constraint on the implied moisture transport, and I'm going to do that based on CMIP6 models. So this is just a table showing some of the results from CMIP6, and overall, so with a warming planet, you're going to get a more intense hydrological cycle. If you sample, the runs at the end of the 21st century, you're going to see a difference. So I picked a corresponding time period from my reanalysis for my state estimation, and the range of moisture transports I get. So this TN is the 40 to 90 degrees north. The range I get is from 0.86 to 0.93 sphere drips, with an average of 0.89. And then in the southern hemisphere, I get a range of 1.03 to 1.25 with an average of 1.1 sphere drips. So if you look at these same quantities in the reanalyses, you're going to get a lot bigger range, and I think that's just because you have these external source and sink terms that are being applied in a reanalysis, so it's not as physically consistent as what you would get in a fully coupled system. So these numbers that I'm using are broadly consistent across the CMIP6 ensemble. So I think that gives some confidence. So for the experiments, I'm using the 1/4 degree MOM6 ocean configuration that was described in AgCroft 2019, initialized in 1982 with World Ocean Atlas 05. And for all the results I'm showing here, there's no salinity nudging. And the reference case with the Mera forcing, so this M denotes Mera force runs and J is for JRA. So for the reference case, I'm using the what we previously used for our mass closure. So that's just constraining the net E minus P over the ocean to be 0. And then for the other experiments with Mera forcing, this experiment M, I brought in, I'm accounting for land storage. And then the experiment M with the asterisks, I'm including this mid-latitude forward moisture transport constraint. And then same for JRA. And then there's another experiment I'm showing with the Mera forcing, but initialized in a different year. And I'm using the SODA reanalysis conditions, TNS, to initialize the model. So this is what I'm getting for those cases with the reference closure, doing it the old way. The moisture transport into the northern hemisphere is about 0.7 sphere drips. And then for when I introduce the land storage, that becomes more consistent with what we're getting from the CMIP models, and with the moisture transport constraint. So in this case, with Mera and JRA, these numbers are the same by design. They're constrained to have the same values roughly, with all the other cases, if I'm not applying that, then this is just kind of what emerges from the model. So Mera is pretty much consistent, with and without this moisture transport constraint. So that's just saying that the Mera fluxes are roughly consistent with the CMIP ensemble. And JRA, you tend to underestimate the northern and southern transports without the constraint. So and then you can look at sort of how much water's the net forcing in the Atlantic Basin. So with the constraints, you get about a half a sphere drip net forcing into the Atlantic north of 40. And then for the Atlantic as a whole, it's net evaporative around minus 0.9. And then there's a difference in AMOC. So the Mera run with everything included here slightly underestimates the rapid estimates with a pretty realistic trend, weakening trend. And then the JRA runs tend to overestimate rapid. And I think the reason for that is in the northwest Atlantic, and I'm just highlighting this here, and this is just taking a particular year. This is 2008, the surface sensible heat flux. And the difference with JRA minus Mera is shown in the bottom. So we tend to get just a lot more surface cooling with the JRA forcing in the Northwest Atlantic. So I think that accounts for this stronger AMOC in this model. So that's with the same hydrologic constraints. This is just a difference in the rest of the boundary conditions that we're using. So I think it's just kind of this stronger AMOC is just accounted for by what's happening up here in the Northwest Atlantic, and kind of have to look at that further. So initializing from the World Ocean Atlas, in the top left, this is the old way of doing it, and the model cools pretty drastically. And then on the top right, with the new closure, you see a greatly reduced cooling. And similarly with JRA, we see a big improvement. One thing to note here is that in the middle panel on the right, this is showing with the new closure and with a Z coordinate. And then this model, instead of cooling, it takes up heat. So this is a well-known issue with the Z coordinate model where we get more spurious heat uptake. So that's just for context. So the difference between these two panels is just the vertical coordinate. But otherwise, everything else I'm going to show here is with the hybrid vertical coordinate. That's isopycnal in the interior. So this is just looking at the same picture, but this is globally, and so the top is for the upper 500 meters. The bottom row columns are for 500 to 1,000 meters. And you can just focus on the solid line here. So that's the volume average over that depth range. And then the left, you have temperature, salinity in the middle, and potential density on the right. And this is oriented with sort of lighter being upward. Potential temperature increases going up and salinity decreases. This is with and without land storage and the moisture transport constraint. The blue line you can see in the black are this is EN4 analysis. You can see that, and I should note here also that everything is referenced from the 2005 to 2018 period. So all these plots are have a zero mean over that period. So with the old case, we start off a lot warmer initially, so we have this drastic cooling that I was showing earlier, and then it kind of settles down after 20 years or so. But we see a big reduction in that initial drift when we introduce the closure, and then it's pretty much on track with the observations. Following around the year 2000. And so that's in the upper 500 meters, and below, similarly, we see this, this large cooling with the old way of doing it. And it's we really knocked down that initial drift pretty substantially. And then for salinity, same story, the salinities in the upper 500 meters are actually quite consistent with the observations. We see a weak increase in salinity over the time period, and then a freshening below, and that's with the new closure. With the old closure, not consistent with the observations. And then same thing for potential density, just much less drift. And then this is looking deeper, particularly for temperature, we have this 0.1 degree cooling that we pretty much get rid of in the 15 to 2,500 meter range and below. So, and a big reduction in potential density drift. Salinity is not so impacted in this depth range, but overall an improvement. And then this is just looking in the North Atlantic. This is looking much better with the new closure. Pretty much applies anywhere I look. This is in the subpolar North Atlantic. This is comparing with the new closure, but just initializing in 1988 instead of 82, and with the SOTA initial conditions. And basically, these lines converge after 15 or so years. They tend to converge. So that's just giving some indication of initial condition sensitivity. So we see similar reductions in that initial drift with both JRA and MERA. In this case here, in this 500 to 1,500 meter range, the JRA looks to be more consistent with the observations. We don't see this warming or cooling initially as much. For salinity, the JRA forcing is somewhat less consistent with the observation. So it's a mixed bag in terms of, it's not clear which data set is better, but I am seeing in both cases a big improvement in that drift. Okay, and this is looking in the subpolar North Atlantic with JRA and MERA. Just to give an idea of the sensitivity. So this is for the 2000-2004 pentad difference with the 2013 to 2017 pentad, the rate of heating in the upper 700 meters. So on the top left, this shows the original, the old way of doing it, and globally averaged is it's minus 0.14 watts per meter squared over the ocean. So that's clearly not consistent with a lot of the observational data, which is shown on the right. The top is, I believe, for EN4, and the bottom is for SODA. They give anywhere from 0.4 to 0.5 watts per meter squared over that depth range. With the new closure, it's about, it's roughly consistent. So we get about 0.36 watts per meter squared. So, and the patterns, you can see the warming in the Indian Ocean, subtropical, North Atlantic, so forth. So there's a lot of good consistency between what's shown on the lower left and what's shown on the right. By this metric, these results are pretty good. So so basically, to summarize, hopefully I convinced you that we made a significant improvement in our ability to produce a ocean state estimation by introducing something which is physically based in terms of hydrologic closure. So we're taking into account land storage, basically. And then furthermore, this methodology, at least in the configurations that we're using, it appears to eliminate the need for this non-physical SSS restoring. And MERA and JRA both showed similar improvements, and there's a large reduction in temperature, salinity, and potential density drift from initialization, pretty much in all basins, and we get a better AMOC representation. So the next steps are, we're working on a 1/12 of a degree configuration with a C348 land component. That's roughly a 1/4 degree land grid. So, and we'd like to repeat this analysis and then also start looking at incorporating other reanalyses such as ERA5. And that's all I have.
Great, thanks, Matt. Keith had a question.
Matt, thanks for that presentation. It's really interesting results. What are your thoughts on the implications of this work for something like OMIP, where you're trying to have standardized forcings for the ocean model, and modeling centers might not have a land model that they can use, or they might have different land models?
Yeah, I think for one, I would like to see the OMIP protocols reflect, the importance of land storage, as to the differences that might emerge from different land models. I mean, I think you'd have to allow for differences, and but I think just to take the additional step of incorporating some sort of land representation, I think is an important one for OMIP.
Okay, Santa?
Matt, thanks for the presentation. I had I was relieved and happy to see that there were not many differences from what you have between MERA 2 and JRA 55 DO forcings. So that was good news for us. reassuring. So have you had any changes to the runoff? Assumably you'll have a different land model and prescription to that, so precipitation, so it may be changing your runoff, or did it? And a consequence of it would be, were there any changes in the sea level or the sea level anomalies? I don't know if you have looked into it or not. And so the reason why I'm asking is also, while providing a bit of an inside story here, is that we are about to produce a new ocean reanalysis, like Mera 2 forced ocean reanalysis for the ocean. And so, that uses, of course, older MOM 5. And so we had to go and reset the global mean sea level all the time. And going forward, of course, we would not want to do that. And that's why I'm asking this sea level question. Thanks.
Yeah, so kind of just the methodology I'm using by construction doesn't, you won't get sea level drift because I'm just setting, global E minus P, that's over land and ocean, is 0 by construction, which is that's pretty much what you would get in a realistic fully coupled system. So yeah, that's how I dealt with that. As far as runoff differences, I mean, I've looked at the major rivers and compared to Diane Trenberth, and roughly, I was satisfied that the numbers I was getting were pretty consistent. Yeah, so just to be clear, like when I'm doing these simulations, I'm not specifying the rivers.
So if
why don't we move on and come back to this in the discussion at the end of these technical points. And I think Ian is going to take over as moderator at this point.
Thanks, Frank. Our next talk is Genevieve Ellsworth. And if you want to go ahead and share your screen.
Okay. Can you see my slides?
Yes, looks good. Thanks.
Okay. So perfect. First off, I'd just like to thank you all for the opportunity to present this working group meeting. My name is Genevieve Ellsworth, and I'm a PhD student in the Geological Sciences Department at CU Boulder, working primarily with Dr. Nikki Lewandowski. And today I'll be presenting a recent research project aimed at quantifying changes in internal variability of phytoplankton with climate change. And this will be specifically using the CESM 1LE as a model testbed. And so this research has been done in collaboration with many other folks, including Tom Marquito at CU Boulder, Kristen Krumhart and Matt Long at NCAR, and Sarah Schlenegger at Princeton. And this work is still very much in progress, so any comments and suggestions are more than welcome. And so just to begin, I wanted to start with a brief motivation for this study. So phytoplankton are important because they're a central component of the marine food web and provide food for higher trophic levels, such as fish. And since they're the base of the marine food web, any changes in phytoplankton biomass, and particularly changes related to any kind of anthropogenic warming, are important at regional scales for fisheries adaptation. And so this map on the right here just shows the change in the distribution of maximum catch potential from fisheries with climate change, with regions of blue showing areas of increased catch potential and regions of red showing areas of decreased catch potential. And you can see that globally, as the climate warms, there's going to be a large scale change in the distribution of fisheries. So in this context, phytoplankton biomass specifically is a really important variable in predicting changes in catch potential in offline fisheries models. And from this perspective, trying to constrain these changes in phytoplankton variability will help us to reduce uncertainty in these marine ecosystem projections. And I also want to mention here that although there are a few different ways of representing phytoplankton biomass in the model ensemble, for the purposes of this talk, we're going to focus on biomass carbon because it's conserved in the Earth system model. It can be used as a proxy for biomass. And as I just mentioned, it's important for offline fisheries models. So as I mentioned, we're going to estimate projected changes in marine phytoplankton variability using the CESM1 LE. And so here I'm just showing a brief validation of the model ensemble for phytoplankton carbon variance by comparing phytoplankton variability that we observe in the real world against what we observe in the model. So this map on the left shows satellite estimates of phytoplankton carbon variability with units of standard deviation. And this is observed remotely with regions of red showing areas of higher variability and regions of blue showing areas of lower variability. And you can see that generally speaking, there's lower variability in phytoplankton in the subtropical gyre regions and relatively higher phytoplankton variability in the subarctic, Atlantic, Pacific, and also in the Southern Ocean. And so when we compare this to the range of phytoplankton variability in the model ensemble over the historical period, which is shown on this map here to the right, you can see that there are similar spatial patterns compared to the real world. So these regions of purple correspond to areas of relatively higher variability and has a similar distribution of high variability regions in the North Atlantic, North Pacific, and regions of the Southern Ocean. And also similarly to the observed data set, the yellow regions, which represent areas of lower phytoplankton variability, correspond to these subtropical gyre regions. So just generally speaking, the CESM1 LE does a pretty good job at representing observed phytoplankton in observed variability in phytoplankton biomass. And although the model tends to slightly underestimate the magnitude of variability in phytoplankton, it's done a pretty decent job at representing these regional patterns of observed variability. So as a first step, we took a look at the global mean change in phytoplankton biomass across all 34 ensemble members of the CESM1 LE. And so this figure here just shows the change in annually averaged global phytoplankton biomass from the historical period through the RCP 8.5 or high emissions forcing scenario. And so individual ensemble members are shown here in the gray lines, and they're representative of the range of internal variability in the model ensemble. And the ensemble mean is shown here in the black line, and that's representative of the externally forced trend. And so you can see that globally, there's a large decline in phytoplankton biomass with anthropogenic warming in this particular model ensemble. And although it's not super easy to see on this plot, there also appears to be a slightly smaller envelope of variability towards the end of the century than towards the beginning of the century. So the ensemble spread is relatively smaller. And we're actually interested in quantifying this change in variance. And so to understand how that range of internal variabilities in phytoplankton is changing with climate change, we quantified the range of internal variability for global phytoplankton biomass using the coefficient of variance. And we calculated the coefficient of variance as essentially the standard deviation across all 34 ensemble members and normalized against the ensemble mean. So essentially we're taking a look at how the spread of the ensemble changes over time. And so this figure just shows that global change in annual phytoplankton biomass variability from the historical period, again, through that high emissions forcing scenario. And as you can see, the range of internal variability in phytoplankton biomass is relatively steady across this historical period from 1920 to 2005. And then there's a significant decline in phytoplankton variability across the high emissions forcing scenario from 2006 through the end of the century. So I just want to mention here that the CSM1 LE isn't unique in showing this decrease in phytoplankton variability with climate change. We also took a look at a few other CMIP5 models and also observed a similar decline across them. So although there's a global decline in phytoplankton variability over time, the changes in both the mean phytoplankton biomass and its variability are pretty spatially heterogeneous. So this map on the left just shows the change in phytoplankton biomass as a percentage change from 2006 to 2100. And the hatched regions show any areas with insignificant changes over this time period. So regions of red show areas where phytoplankton biomass is increasing, and regions of blue show areas where phytoplankton biomass is decreasing. And generally, you can see a decrease in phytoplankton biomass across most of the subtropical gyre regions, while you see small increases in biomass in the Arctic and across a few regions of the Southern Ocean. And so in comparison, the map on the right shows the change in phytoplankton biomass variability, again, as a percent change over the same time period. So regions of red again show increasing variability, regions of blue show decreasing phytoplankton variability. And in this plot, you can see definitely more mixed trends in the subtropical regions, and a general trend toward decreasing variance in the Eastern Equatorial Pacific, increasing variance in the Eastern Equatorial Pacific, and decreasing variability in the North Atlantic and Northern Pacific. So I just want to emphasize here that these regions in the North Atlantic and the North Pacific are really important for fisheries, and any large changes in phytoplankton variability in these regions are important to consider for any local projections of the marine ecosystem in these areas. So now I just want to transition to identifying these different regional drivers of these changes in phytoplankton variability. And as I mentioned before, particularly in these regions that have high fisheries catches. And to do that, we're gonna use some ecological provinces to isolate different regions, especially in the North Atlantic and North Pacific, so that we can start to take a look at mechanisms driving this change. And here I just want to emphasize as well that it's really important to consider which type of phytoplankton is dominant in each of these regions of interest when we're identifying possible drivers. So the model ensemble we're looking at includes the representation for 3 different types of phytoplankton, diatoms, diazotrophs, and small phytoplankton. And as you can see from this map, different types of phytoplankton dominate in different locations. So diatoms tend to dominate in these regions in the North Pacific and North Atlantic, as well as in the Southern Ocean. Whereas small phytoplankton seem to tend to dominate nearly everywhere else in the subtropical gyres. And diazotrophs, since they're generally present at such low concentrations, they don't tend to dominate anywhere. So as we move forward and we're considering the different drivers of phytoplankton variability in these important fisheries regions, we'll be taking into consideration the dominant type of phytoplankton in each of these regions as well. Okay, so just to start with, I want to begin with the most productive fisheries region in the Atlantic Basin, which is just outlined by this, this orange box in the upper left-hand corner. And so in this region, if you'll recall, we're going to be focusing on diatoms because they make up the largest proportion of phytoplankton in this location. And what we were interested in doing is we were interested in trying to quantify the contribution of the different ocean variables that are known to affect phytoplankton growth on any changes in the variance of diatom biomass. So the variables we included in our analysis included both bottom-up and top-down controls on phytoplankton growth. So those bottom-up controls include things like light, temperature, nutrient fluxes, and mixed layer depth. And top-down controls would include mostly zooplankton grazing. So in order to quantify this relationship between diatom variance and these different variables, we performed multiple linear regression analysis on linearly detrended anomalies. And this produced regression coefficients between diatom carbon and the different variables that contribute to changes in diatom biomass variance. And then we used these different regression coefficients to help reconstruct the contribution of each of these driver variables to diatom variance between the beginning of the century and the end of the century. And this is over the RCP 8.5 or high emissions forcing scenario. So this bar plot here shows how each of these different variables contribute to the change in diatom variance. The blue bars show variability at the beginning of the century, and the green bars show variability at the end of the century. And so on the leftmost set of bars in the plot, you can see the change in diatom variability, and all of the sets of bars to the right show changes in the other variables that we're taking a look at. So for this North Atlantic region, there's a large decline in diatom variability between the beginning of the century and the end of the century. And the largest contributions to this change in variability derive from the decline in diatom grazing variability. And there are smaller contributions to this change that derive from changes in solar flux, sea surface temperature, and the nutrient infection terms. So when we finished this analysis, we were really surprised to see these top-down controls seeming to dominate these changes in variability in diatoms. So moving on here to the most productive fisheries region in the Pacific Basin, which is shown just in this orange box up here. Again, we're focusing on diatom phytoplankton because they're the most dominant type of phytoplankton in this region. And again, we did the same approach where we used the regression coefficients from the MLR analysis to reconstruct the contribution of each of these driver variables to the change in diatom variance between the beginning of the century and the end of the century. And so this bar plot shows the same thing, where it shows how each of these different variables contribute to the change in diatom variability. So again, for this North Pacific region, you can see that there's a large decline in diatom variability between the beginning of the century and the end of the century. And again, the largest contributions to this change in variability derive from this decline in diatom grazing variability, whereas you see smaller contributions coming from changes in solar flux and phosphate advection. So again, we were really surprised to see the decline in diatom grazing variability as the dominant contributor to this decline in diatom carbon variability. And finally, just to move on to the last region, which is the region in the Southern Ocean. So this isn't a particularly important fisheries region, but it is an important area for global biogeochemistry. And in this region, we're focusing on total carbon because both diatoms and small phytoplankton are equally dominant in this particular area. So as you can see from the same bar plot, for the Southern Ocean region, there's a relatively smaller decline in phytoplankton variability between the beginning of the century and the end of the century. And again, the largest contributions to this change in variability derive from a decline in diatom grazing variability and also a large decline in small phytoplankton grazing variability. So overall, I'd say the change in grazer variance was pretty surprising to us as a possible driver. And we're not still exactly sure why that's happening. It could possibly be related to changes in the variance of their food source or to changes in temperature variance, but definitely open to hearing more ideas on why this might be happening at a mechanistic level. So just to conclude, there's a decline in global phytoplankton biomass variance in the CSM1 LE with warming, and this is reflected by similar changes across CMIP 5. These changes in biomass variance vary in different regions of the world's ocean, and surprisingly, phytoplankton grazing, or this top-down control, seems to drive variability in phytoplankton in some of these important fisheries regions. So thanks for your attention, and I'm happy to take any questions or suggestions.
Great talk, Genevieve. Does anyone have any questions? So Dan Imran has one.
Hi, Genevieve. Thanks a lot for a really cool talk. One thing, I guess just a comment, we saw a talk in the CGD seminar a couple weeks ago by Nicola Maher, who's a postdoc at CU. And she's also doing things looking at non-stationarity and changes in ENSO variance. And anyway, maybe you guys could chat and there'd be some overlap. I was wondering, so I'm not a BGC expert, but one of the things you said at the end in terms of making mechanistic attributions, in terms of, I was wondering to what extent some of these bars you had in your plot could be correlated variables. And if looking at a multivariate, how multivariate covariances change in time might be a way to try and tease apart some underlying relationships.
Absolutely. So in our analysis, we haven't been including these secondary terms for our MLR approach. So, but as you mentioned, a lot of these different variables are related to each other through different relationships. So for example, the grazing term is related to changes in temperature because they graze faster at higher temperatures. So teasing apart also that relationship between the grazing variance and the change in temperature variance is important. So I think going forward, we need to kind of redo this analysis also, taking into account those secondary relationships rather than just the primary relationships between the different variables we got from our initial MLR approach. But I think that's a good idea to help tease apart these relationships a bit more, since there are many interrelationships between the different variables. So.
Right. Yeah, I point you to the snapshot EOF literature too, where I think people are doing this within physical variable space.
Definitely. Yeah, it's a great suggestion, and one we'll be exploring next, I think, since there are so many interrelationships.
Thanks again. I think instead of further questions, because we are about 10 minutes behind, I'll just ask if Sam is around, and Genevieve, if you could stop sharing. Sam Mogan, I think you're next.
Yeah, hi. Is that shared now?
Yes.
Awesome. Good morning, everybody. My name is Sam Mogan, and I'm a PhD student in the Department of Atmospheric and Oceanic Sciences at the University of Colorado Boulder, working with Nikki Lewandowski. Today, we're going to be using the CESM Forced Ocean Sea Ice Reconstruction, or FOSSE, to understand the effects of a marine heat wave, the North Pacific Blob, understand the effects on regional biogeochemistry, and break down what exactly drove those changes, at least from the model perspective. This project grew out of an ongoing effort to investigate predictability of ocean acidification and extreme events using Earth system models. This is work we're kind of continuing on. Many thanks to all my collaborators and to NOAA CVP for funding my work. So to start, what exactly was the North Pacific Blob? It was an extremely strong and long-lasting marine heat wave spanning a roughly 3-year period in the Gulf of Alaska. It was driven by what was termed the ridiculously resilient ridge, which was a high-pressure system that sat over the area, leading to rapid and very extreme warming, primarily due to a decline in evaporation and decline in import of cold waters from advection. There was just less wind in the region. The plot here is showing the development of the blob in a gridded observational product developed at ETHC in Switzerland. This anomaly is basically a bimonthly anomaly calculated relative to bimonthly base period averaged over 1985 to 2010. If you note in the top row, you can begin to see the blob form starting in late 2013. And by January, February of 2014, we see the really, really strong blob-shaped pattern appear. By the winter of 2015, the blob has sort of moved and become more coastal signal, migrating all the way down to the California current system. So while the physical drivers and impacts of the blob are relatively well understood, the biogeochemical effects are relatively understudied. The latter arc-shaped coastal pattern was in a much more heavily observed region down in the California current system. So we have an idea of the effects of BGC down there, but the early, very strong blob-shaped manifestation is understudied when it comes to biogeochemistry. So in this study, we're going to focus on this early manifestation, particularly the winter of 2014, so January, February of 2014, this bimonthly region, and try and understand what exactly is going on with biogeochemistry here. So how are we actually going to approach this? Well, we started with observations and just tried to figure out what we would see with that. So we looked at direct observations. The only real direct observational signal we have is from the Papa Bui array, which is relatively nearby to this blob-shaped pattern. And it's the only record in this Gulf of Alaska that's continuous during the time period that has both carbonate chemistry and oxygen measurements. We also looked at gridded observations, again, the Ocean Soda ETHC, which is developed in Switzerland, surface gridded product developed particularly for the study of carbonate chemistry. And it gives us an idea of this picture of what's going on in BGC here at the surface. And these observations were not really giving us enough information. So we moved and looked at the CSM DPLE FOSSE. It's a model reconstruction developed in the development of the Decadal Prediction Large Ensemble. And it's basically the ocean sea ice model run with historical land and atmospheric forcings, giving us a best guess at what's happening in the real world. And it allows us to look at biogeochemistry beyond the surface and get a picture of what's going on with driving these changes. We want to start with just showing you what does the model reconstruction actually suggest happened during the blob. So on the left, this is SST anomaly at the surface. We see a really strong SST warming associated with the blob. It's a marine heat wave, so this is what we would expect. The hatching here is indicating significance at a 2 sigma level. And then we turned to some biogeochemistry. So omega aragonite here is our stand-in for understanding ocean acidification. An increase in omega aragonite as observed in the Blob region means that acidification went down at least temporarily. And we also looked at dissolved oxygen, and we found a significant decline in dissolved oxygen during the Blob period. So one good thing, a decrease in the acidification signal, and a bad thing, a decline in regional oxygen. And this again is the January, February of 2014 relative to a base period of 1985 to 2010. We know what the model is suggesting, but I need to prove to you that the model is actually doing a good job relative to the observations that we do have. So on the top, we started looking just at SST, trying to understand and compare if it's working. The top left panel is showing SST anomaly in our gridded observational product, has very similar extent spatially to our model output. And we also looked and just took a matched point from the gridded observations and our gridded surface model output and compared that to Papa Buoy data. So this is just the SST anomaly with climatology or seasonal climatology removed. And we found a very similar signal in all three data products for SST. We see a spike starting in the beginning of the Blob period in this light gray, and then during the winter of 2014, early winter of 2014, we see, which is the dark gray here, we see a really strong spike in SST in all three products. Again, for omega aragonite, we also compared, and we saw a really similar spatial extent in our gridded observations, and also saw a very similar spike during the Blob period from all three of our data products. So the model seems to be working, and we can now kind of start exploring biogeochemistry in a little more depth. We also did take a look at some other system model reconstructions to check and make sure it wasn't anomalous that this was appearing in CESM FOSSI. So we looked at the Meteorological Research Institute of Japan and the Norwegian Earth System model and found very similar signals as in our observations. CESM FOSSI did a better job in some ways than these other ESMs, especially for oxygen signals. The magnitude of change in these other system models just does not capture the spread that we found in observations. So we know that FOSSI is working, and here again is sort of what's happening. So we have a bad thing and the oxygen going down, and a good thing in the mitigation of ocean acidification. So we're going to start and investigate a little bit more about this good thing, the mitigation of ocean acidification, at least temporarily. And we're going to start by breaking down what omega aragonite really represents. So omega aragonite is just the dissolved carbonate over carbonate at saturation. So it's the saturation state of carbonate, the aragonite form. CO3 at saturation is not really going to change. It's going to be relatively conserved in the blob since it's such a rapid event. This value would not change, but we would expect the CO3 to change. And CO3 is roughly a function of alkalinity of the water and dissolved inorganic carbon or total CO2 of the water. So we took these, what we know is driving changes in CO3, what could potentially be doing this, and we used a CO2 system solver to determine linear relationships between all variables and the dissolved carbonate values. So we looked at alkalinity and DIC, and we also looked at the effects of temperature, freshwater input, and salinity inputs. So we took this linear relationship, and the slope of this line was used to quantify how much of a change in a given variable would have contributed to a change in CO3 as noted in the Blob model output. So the changes in the CO3 on this plot, we found that DIC was really driving the largest amount of change and leading to this dramatic increase in carbonate associated with the Blob, which led to an increase in the omega aragonite value and a decline in the acidification signal. So moving forward, we're going to focus on DIC and try and understand what's driving changes in DIC. One major advantage of this model reconstruction is the ability to look at the full water column. So we looked at depth just to determine how deep this signal would extend significantly. And we found relative to the base period, which is the green line, the blob line, extends down to about 100 meters and is significantly different than our base period. So the signal is not just trapped in the top 5 to 10 meters of the water column, it's propagating down to about 100 meters. And since we know if this signal is down to about 100 meters, we want to understand the processes and look at the integrated fluxes to understand how the blob is affecting DIC. So we're going to use these output terms of tendency to understand this change. So starting at the top, air sea flux is just the amount of carbon flowing into the region, the water column from the atmosphere. The black is showing our base period and the red is showing our anomalous blob values. And we see very little change to the air sea flux during this period. Carbon is not a super temperature sensitive dissolved gas. So especially in this really rapid short-term change, we're not going to see a huge change in the air-sea flux. Circulation tendency here is showing changes, basically all changes in advection of water into the region. So this includes advection, subscale circulation processes, including isopycnal transport and dipycnal diffusion. We actually see a decline in the import of carbon-rich water into the region. And this is likely a result of stratification, but I'll talk a little bit more about that in a second. And we also looked at the biological tendencies of carbon and found a slight increase in the import of carbon from biological processes. But again, this, in terms of magnitude, it's much lower than the circulation tendency. So with circulation tendency, what we're really using to explain this is the decline in import is coming from the fact that in the Northeast Pacific, deep water is very carbon rich and the surface water is relatively carbon depleted. And when you have a really strong warming signal at the surface, you're going to increase stratification and decrease vertical circulation. So there's going to be less carbon rich water flowing up from depth into the surface column. And this stratification signal does appear. This is just a change in the rho over time. So rho 200 minus rho at surface density. And we see an increase associated with, in the light gray, we start to see an increase, and especially in the winter of 2014 in our time period of interest, we see a really strong increase in stratification, which would lead to a decline in vertical circulation. So we know that stratification is really driving the effects in the decline in ocean acidification during this blob period. We want to understand why dissolved oxygen would be declining so significantly. Again, with model, we looked down at depth and just tried to understand how deep the signal goes. And as with our carbon signal and our acidification signal, we're seeing it down to about 100 meters. But unlike carbon dioxide, oxygen is highly temperature dependent on really short-term timescales. So the effects of this warming would be felt on the amount of dissolved oxygen present. So knowing this, we wanted to just go ahead and determine a linear relationship between oxygen and temperature we used Sarmiento and Gruber and Turri et al. 2018. We calculated this linear relationship and used the observed change in temperature to basically back out a residual oxygen and trying to determine, is this decline in oxygen purely from the temperature effects? And looking at this vertically, on the left, we have our original vertical column of oxygen, and on the right, we have our oxygen residual. And what we found is, while removing the temperature effects from oxygen basically makes the blob in the base period a lot more similar, we can still see some significant change during the blob period that's not purely a result of this temperature relationship. So as with acidification, we wanted to turn to our integrated top 100 meter fluxes to try and to see if we can explain what's going on here. So again, air-sea flux, the amount of oxygen flowing into the water column from the atmosphere, we actually see a sharp decline in the air-sea flux, the import of oxygen from the atmosphere. And this is really a temperature dependence thing. So this is something we've already sort of thought about, but it is the largest term. Circulation tendency, we actually see a decline in the export, or however you want to think about this, the export of oxygen-rich water. Basically, so we're seeing more oxygen in the region from circulation. And again, this is a result of stratification. In the Northeast Pacific, deep waters are going to be really oxygen depleted, and surface waters are going to have relatively high oxygen. When there's stratification, there's going to be less vertical mixing, and we're going to see less oxygen depleted water flowing into the surface from depth. We also see some increase in the export from biology, but really the largest change is coming from this air-sea flux. So oxygen can primarily be attributed to changes in temperature and biological export. So in conclusion, the blob is associated with relief of ocean acidification, but lower oxygen concentrations. The relief of ocean acidification in the blob is coming from reduced upwelling of carbon-rich waters. And this decline in oxygen is primarily a result of the influence of warming on the air-sea gas influx. So we hope to apply what we've learned here and complete similar work on other marine heat waves identified in our data sets. We're trying to understand if this mitigation of acidification is something we can expect with marine heat waves going forward, or if this is just kind of a situational thing. And eventually we hope to investigate the ability of near-term initialized experiments in CSM to predict these extreme events, especially as they relate to ocean biogeochemistry. And with that, I can take any questions. Here's a link to our preprint as well in GRL.
Great talk, Sam. Questions? Bill's unmuted and he's got his hand up. So go ahead.
Yes, both. Yeah, thanks for that. Papa is always fascinating in that area, but I have two questions. One, I mean, the ocean station Papa is iron limited in its biology, right? And production. And so I didn't see anything whether iron has changed, whether this big blob results. I would have thought things would have, because you wouldn't be getting storms and dust in from the Gobi, that you would actually get iron limited. And I was wondering whether that happened. And the other thing I wanted to know about is the DIC budget seems to be really positive. And so is DIC increasing in time that fast continually? That was my other question. Is DIC just growing without bound? So that's the two questions.
So the first one about iron limitation, we ended up looking at productivity just generally in the blob and trying to see if there was an anomaly, and spatially there was really no clear pattern. So I'm not sure how the iron really played out, but we haven't looked at that specifically. And then with DIC, I mean, we have an increase in carbon sort of in the just due to acidification in the region, but where is this? Sorry.
There.
Sorry, struggling here. But I'm not sure. I think there's just generally going to be an increase in DIC, the DIC budget over time. And I think that's what this is suggesting.
All right, Keith has a question.
Hey, Sam, thanks for that, sharing this analysis. It's really nice work. I'm curious if you've looked at ideal age as well. That it seems like you might be coming up with, from the analysis of the BGC tracers, hypotheses about what you would expect to see in age, and then you can check to see if the results in age are consistent with those hypotheses.
No, that's a great idea. That's something we haven't really considered or looked at, but that's something I'm really interested. That sounds cool.
All right, we made up a little bit of extra time. If there's any questions, we could maybe take one more.
Can I just respond to Bill Large's question?
Sure.
This is Nikki. Hi. Bill, that budget that Sam created is for the wintertime. So when respired carbon can come back up, because that's when the blob manifests most strongly. So there is, of course, an anthropogenic increase in DIC every year. But because we're looking in the winter, that's the time when you re-entrain carbon-rich water from the deep to the surface.
Thanks.
Yeah, thanks for clarifying. All right, our next speaker is Baylor Fox Kemper. Are you ready, Baylor?
Yeah, I'm ready.
All right. You want to share screen?
Sure. Still there. Haven't been disconnected. All right.
It's good.
Okay. So I can't remember if it was last year or the year before, but anyway, in a recent OMWG, I took the opportunity to complain about how terrible it was to be involved in the IPCC. And so by contrast, sometimes you see some things that are not so apparent until jumping into that context. And so I wanted to talk about that today, which is a project that was led by Galen Hall, who was an undergrad, and he did a really nice analysis that was really informed by a lot of the toolkit that we were using for the IPCC. And I think this has turned out very nicely. We have a submitted paper, which I'm happy to share if people would like to see it. So anyway, there's this very long title, Regional Mixed Layer Depth, Climate Diagnostic, Emergent Constraint. So lots of things. I hope that will become clear as I move on about what all those pieces are. Okay, so in the, you probably have all seen these kind of energy and sea level budget breakdowns. This is, a nice way of thinking about what the role of, what an important role of the ocean is in both the energy cycle and the sea level. And essentially, what matters here is how much the different layers of the ocean are warming up. The 0 to 700 meter, the 700 to 2000 meter, 2000 meter and deeper. And it's true on both sides of these, in both of these budgets. That's one part of the thinking that got us where we went. And then we were also really interested, as I've talked about it a gajillion OMWGs before, the mixed layer. And so the question is okay, so there's 0 to 700 meters, and maybe you could even break it down to 0 to 200 meters warming of the ocean. And then there's the mixed layer. The mixed layer is kind of that same ballpark of depth. So if you're thinking from the perspective of permafrost, like what's the active layer of the ocean? Where is the ocean warming? And we know on very short time scales, that's coincident with the mixed layer. But on the decadal to centennial timescales, of which you might think about for climate projections, is that still true? So that's another thing to keep in mind. And if you were going to make a budget for that warming at the surface, this is a nice figure from some folks at the Hadley Center. You might do kind of a trend birth style diagram where you take the sun and you have reflections, and then you have outgoing long wave, and you have clouds and greenhouse gases, all that stuff. And the big energy reservoir here is really the ocean warming up, and they have drawn a line here to indicate that the mixed layer would be the thing that goes together with the surface atmospheric temperature. So in a sense, what it means to warm up the surface atmospheric temperature is to warm up the mixed layer. And that was essentially where we got started. And the last piece of this story, which of course, it's always good to mention the Nobel Prize when you have the opportunity, is what experimental framework might we have for this? Well, there's the Hasselman and Franken Newell model, which is essentially a temperature change of a mixed layer with a fixed mixed layer depth under a random atmosphere and a restoring force. And so you can solve this stochastic differential equation forced by the random atmospheric forcing. And you get, if you express it in the power spectrum, you get something like this on the right-hand side, where you can see the frequency of the response. And then depending on what lambda is, you get different amounts of low frequency variability. So if all this low frequency stuff is our climate variability and our random forcing is coming from the atmosphere, that's the standard thinking about how a model like this responds. But really, this isn't a great model for that process because it requires the mixed layer to be fixed in time. And we know that the mixed layer changes seasonally, diurnally, and decadally. We know that the mixed layer varies across models, and its sensitivity and the SST response varies across models, even when they're being driven with kind of similar random atmospheres. So there's a lot missing that we might want to think about. And then the connection, so if we have this kind of active layer conception, there is an active layer, it's warming up. How does that relate to things like the AMOC and the southern overturning, which simple models like Anand's nice, beautiful model, which relates those overturnings to the movement of the picnic line between an upper light layer and a dense layer with eddies and Ekman and sinking all put in together. So anyway, this is sort of the conceptual framework that we were coming at this problem with. So let me tell you what Galen figured out. So the key question we asked was, does the mixed layer affect climate change? And in particular, does the mixed layer relate to climate sensitivity? And so we picked up on a thread following a lot of work that was started by Jonathan Gregory, who also noticed that the active layer of the ocean was definitely not coincident geographically with the mixed layer, even though they're kind of conceptually entangled in our mind. And then a lot of nice work out of GFDL from the Winton paper, and then back to the Europeans for the Geoffroy et al. Paper. And they expand on the Hasselman and a model a little to have a shallow layer and a deep layer, kind of reminiscent of what Anand talks about. And then there's a coupling coefficient between them. So this gamma is the coupling between the upper layer, which is the rapid warming one, and the deep layer, which is the slow to warm layer. And they can be coupled together. And then there's this efficacy factor, epsilon, which essentially says if you have an anomaly in your upper ocean, does it get resolved by exchange with the deep ocean, which would be epsilon equals 1 case, or by exchanges with the atmosphere, cloud feedbacks, and other things, which is epsilon not equal to 1 case. And then there's the same lambda that's going there. There's atmospheric forcing or top of atmosphere forcing, depending on which temperature you're interpreting this to be. And then there's a heat capacity of the surface ocean, heat capacity of the deep ocean. So this is slightly different in terms of where the volume ends up, because this heat capacity is an extensive one. So it depends on how deep that layer, surface layer is versus the deep layer. And so this is, so there's this, Geoffroy really perfected this, but going back before, you can take a climate model and you can train it and find all the parameters in this model. And then Matt Palmer and others have shown that it actually does an excellent job of predicting or projecting ocean warming. And I should emphasize, this is a global mean temperature. It is not temperature by region. And also the global mean thermospheric sea level rise. So this emulator, this toy model, can reproduce the climate model pretty well for projections. And so you say, well, okay, that's fine. Now we could always just train that against climate models and off we go. But here's the problem. Lambda, epsilon, gamma, CS, and CD are not observables. The way we determine those parameters is through matching them to a model. And you have an early time where you have a rapid acceleration, which tells you about the parameters of the surface layer. And then you have a later time, slower, where you're getting parameters about the exchange coefficients and the size of the deep layer. That's not really the way we would like to do this, because we'd love to observe something that informed us about these so that we'd know whether the two-layer model, this little model, was biased versus observations, or in turn, whether the CMIP model that this two-layer model was trained against was biased versus observations in an interesting way. That's where the mixed layer comes into the game. Okay, so we can use the mixed layer at depth as an emergent constraint. What I mean by this is we take the mixed layer in the CMIP model in 3 different regions. And it turns out this doesn't work at all if you take the global mixed layer depth. You have to take it in a North Ocean region, a tropical ocean region, and a Southern Ocean region at the minimum. You probably could do a better job by adding more, but these 3 were ones that we found were pretty helpful. And if you do that, these parameters in the two-layer model that come out from the training against a CMIP model where we have diagnosed the North Ocean, tropical ocean, Southern Ocean mixed layer depth are strongly correlated against those 3 mixed layer depths. So we can use the mixed layer depth as an emergent constraint on those parameters. Furthermore, we can use the mixed layer depth biases as something that we could correct for in the two-layer model, even if the biases were uncorrectable. And then finally, there's this little superscript I, which is a really amazing part, is these parameters, which are not time dependent and predict the two-layer model and therefore the CMIP model long time scale projected outcome for warming in the surface ocean and the deep ocean, are predicted by the initial mixed layer depth in this model. And I should say this is predicted within every model, but really the way we detected it was we took the whole or a good fraction of the CMIP ensemble and examined these different parameters, and then we looked at the intermodal scatter of the mixed layer depth in these 3 regions, related that to all of the parameters in the two-layer model, diagnosing a two-layer model for each of the models in the CMIP ensemble, and that's what you get. So let's get a little bit more physical about what this means. If we look over here to the right-hand side, the left-hand column here is the correlation between ocean warming and the surface, the North Ocean in the upper panel, the tropical ocean in the middle panel, and the Southern Ocean in the bottom panel. And like you would expect, the North Ocean mixed layer depth has a lot to do with AMOC. And so the warming of North Atlantic deep water is directly related to the North Ocean variability across the model ensemble. There's also this kind of deep water feature, which is kind of interesting. The tropical ocean mixed layer depth behaves a whole lot like the Hasselman model, and that there's just warming directly underneath where that mixed layer depth is. And the heat capacity of that surface ocean warming is essentially directly related to the mixed layer depth directly above it. And then here's the reason why you can't use the global mixed layer depth for this plan, the Southern Ocean mixed layer depth. correlates with a cooling of the North Atlantic deep water, reminiscent of a seesaw-like pattern, and a warming not only of the intermediate waters that are coming out of the Southern Ocean, but also a kind of global upper ocean warming. That's what happens to the heat pattern, but you also, since we can train this two-layer model against all of these different outcomes, we can look for correlations between, say, the North Ocean and the surface to deep water exchange, which is through this AMOC style mechanism. There's a pretty good correlation between them. Because the tropical ocean has an ocean warming, but also a cloud feedback involved, there's a tropical ocean mixed layer depth correlation with the efficacy parameter, which is that one that I said balances between the exchange of surface and deep and the cloud feedbacks and other atmospheric feedbacks. And then the Southern Ocean actually nicely correlates with the overall climate sensitivity, equilibrium climate sensitivity. You put these all together, you get a big matrix. Sorry, I'm just zooming in one at a time here. You get a big matrix of all the parameters, and you get cancellatory effects between the North Ocean mixed layer depth and the Southern Ocean mixed layer depth, because their North Atlantic deep water impact is in opposite directions. So you really need to separate those out into two different regional mixed layer depth emergent constraints. You get a big matrix, you go like this, you're looking at correlations between things like the mixed layer depth. Here's the mixed layer depths and all the global, north, tropical, southern, and the bold here are the ones that are statistically significant versus a student t-test. And you can see, and the asterisks are significantly correlated at a lower level of correlation. You can see that as you change these parameters, you change things about the AMOC, you change things about the mixed layer depth, and then those have feedbacks again back onto the climate sensitivity and the transient climate response of the two-layer model, which we know is already a good predictor of the climate sensitivity and the transient climate response and the thermospheric sea level rise of the full CMEP model. So what does that mean? That means we can push the two-layer model from its, or the ensemble of two-layer models, by correcting each ensemble, CMIP ensemble member's mixed layer depth toward the observed mixed layer depth from Argo, and thereby reduce the ensemble spread in climate sensitivity. The thin lines here shows the raw CMIP ensemble, and the darker lines show the mixed layer depth corrected CMEP ensemble for the 1% CO2 warming deck experiment and the 4 times CO2 experiment. And you can see that by the time we get out here to when we would evaluate an equilibrium climate sensitivity, we're getting a pretty substantial reduction of about 40% in the climate sensitivity. It's a little bit lower, about 20% in the transient climate response at the end of the 1% CO2 increase. And remember, this is not the mixed layer depth evolving in time. This is based on correlations with the mixed layer depth at present day climate. So the mismatch that's being corrected is for observable emergent constraint today of mixed layer depth, projecting to the 4,000 year 4,000 climate sensitivity. It's rather complicated to figure out what the linear algebra is to invert from the CMEP ensemble to different constrained ensembles. And we tried a lot of different things with Monte Carlo and bootstrapping and et cetera. This just shows you that it isn't too sensitive, that reduction from the big ensemble scatter into the emulator ensemble prediction is pretty robust for all of the different parameters of the two-layer model, regardless of the method we use. And I will skip that. And so cool, this is great. We can do this. We could train a two-layer model against, we can use the mixed layer depth as an emergent constraint. We can try and improve the physics of the mixed layer as modeled in our forward CMIP models. And we can have a sense that the climate sensitivity of those models is going to become a better prediction through that process. So many of you remember Ching's thesis from a couple of years ago, where we were comparing lots of different mixed layer mixing schemes and then trying to figure out what their impact was. This is the impacts that they would make on climate sensitivity thermospheric sea level rise. Abby's theory, which has already been talked about in a bunch of the different talks for how wide the fronts should be and where they're arrested and why it matters for mixed layer depth. Similarly, it allows us to bring these sub-mesoscale, small scale features on through their impact on regional mixed layer depth into the climate sensitivity, large scale climate impacts in a quantitative way. And I will skip over just redescribing what Abby's point is. Just to say that similarly, whenever we make a map like this of control and perturbation experiments, we should be able to extract an impact in terms of climate model sensitivity in the end. That's it. Thank you very much.
Gokhan, want to go ahead?
Yeah, Baylor, thank you for the talk. And can you expand upon a little bit about the timescales that you are talking about? Because as you know, Gregory method is effective climate sensitivity. It depends. I mean, if the results of that will change depending upon what timescale you're interested in. And in this case, you indicated that your mixed layer depth comes from a present day simulation, but when somebody runs 1% or 4 times CO2 runs into the future or longer, then there will be adjustments in the mixed layer depth and everything, and that will impact the uncertainty. So can you, say a little bit more about that, I guess?
Absolutely. So the 2-layer model is simpler than a CMEP model, and it has a clear definition of climate sensitivity, which is just its end state, and its TCR, which is evaluated the normal TCR way. So we're using the 2-layer model to make our climate sensitivity estimates. So there's no uncertainty about what definition we mean in 2-layer model world. What we noticed is that the bias in mixed layer depths was fairly independent in time. So if a model had a deep southern ocean, it tended to continue having a deep southern ocean on and on and on and on throughout the run. So what that means is that we didn't actually need more information about future mixed layer depths because that was already encoded in the initial mixed layer depth biases. So that's what I mean by the initial mixed layer depth is a code for the future behavior of the model because that ordering of bias doesn't change very much.
Okay.
There's a beautiful paper by Gerhard Krinner that says a similar thing about the pattern effects, that once a model's got a biased pattern effects in air sea flux, it doesn't tend to change it as you go into the future. And so what that means is you can do modern day evaluation of versus observations and know that at least in that model will continue influencing as it goes on in more or less the same way. But yeah, for sure, that's an important distinction. But if we want an emergent constraint, we have to be able to observe the phenomena. And so the key here is that we have to use present day mixed layer as an emergent constraint on the model. And none of those 2-layer model parameters are observable. So that's the key wrench to get us into the business of connecting mixed layer depth into climate sensitivity.
Okay, thank you.
Yeah.
We have plenty of time because there's no talks after this. So I think we'll be able to get to all the questions. I want to first read out Nikki's question from the chat just so that people on YouTube know what we're talking about. So Nikki says, Baylor, have you considered expanding the analysis to include also carbon, TCRE in parenthesis, i.e. using MLD as an emergent constraint for ocean carbon uptake / inventory? I'm impressed with the global upper ocean sensitivity to the Southern Ocean MLD.
Nikki, I would be very happy to talk with you in greater detail about exactly that. So there is a whole relationship between the uptake processes of carbon, which is pretty clear, versus the uptake processes of heat. And so Bronselier and Zana did a nice story of how you label the water masses and all that. And because they're both air-sea flux processes and are therefore probably affected by upper ocean mixing, sure, you should be able to do something almost exactly the same on the carbon budget that we did on the energy budget. I have no idea if you end up with the same corrections or the same biases, but we'd have to look through the ensemble looking at, I don't know, whatever, area integrated DIC or something like that, and doing the backwards work to do it. There might we'd have to do something like a pH budget for this. I mean, there's a lot of things to think through. So yes, it would be great to do it where hopefully, knock on wood, if the reviewer is in the room, please let us go through in the next pass. We will hopefully publish this paper very soon, and then we'll be able to expand. But yeah, I'm busily writing proposals and stuff to do more. So happy to talk more with you about it.
All right, Dave, do you still have a question?
Yeah, thanks, Baylor. That was a great talk. I'm a PhD student at Caltech working with Andy Thompson and Tapio Schneider, and I'm kind of doing a similar work where I'm coupling in energy balance model to a conceptual model of the overturning circulation. And I wonder if you took the same framework, but instead of coupling it to the two-layer kind of energy balance model, you did it with like Laura Zana, David Marshall's maybe conceptual model of the overturning, and added some dynamical features. Have you thought about doing that? And if that might provide similar answers?
I suspect it has to. I mean, like once you've done this relationship between the map of the warming patterns and those regional mixed layer depths, like what conceptual model you have that has the ability to manage those like large scale warming patterns probably has to have a similar kind of tight relationship. We used the two-layer model because we were thinking Hasselman in the beginning, and we wanted to say, I thought we were just going to discover Hasselman, like that was what we were going to do, but it turns out that Hasselman only works in the tropical ocean. It doesn't work in the extratropical oceans, which in retrospect maybe I should have guessed, because that's what AMOC and southern overturning are all about and why they're not just a mixed layer process. But it took us a long time to pull those pieces out. But I think, yeah, I mean, building to a more complex conceptual model with still enough limited parameters that you could reasonably do this kind of matrix of correlations. I don't see why that would fail on other conceptual models. It would just be a different approach. I should have said too, there's a gajillion other things other than mixed layer depth that are probably important and inform the climate sensitivity. We're going after mixed layer depth because that's what my group works on. So
cool,
yeah.
Thanks. Yeah, it was really cool work.
Justin, I think you're next.
Baylor, thank you. I wondered if there's anything to learn from comparing the low resolution CMIP style models with high resolution like CSM or high res MIP, and because they have very different mixed layer depths, and we can try and argue that they're more realistic. Particularly, they're very different in the Southern Ocean and the North Atlantic and subpolar gyre. So is there anything extra to learn from the high res models?
That's a really interesting idea, Justin. So Takaya Uchida is leading a paper right now looking at submesoscale permitting models in a few locations. Global high-res models would be interesting. I mean, I don't know the extent to which their heat uptake and kind of more standard long time scale, centennial scale climate change parameters are even well understood. But using a two-layer model as a intermediate step to match those pieces so that then you get the equivalent, expected millennial scale warming would be interesting to try. We didn't mess with that because we were basically just using whatever we could find in the Pangeo repository. And so that was really our defining constraint, was what models had uploaded the variables we needed there. So that was coarse resolution CMIP. It would be really interesting to try and do this again with high-res models.
And the IIS project produced long climate runs to look at climate sensitivity. So Ping Chang and
yeah, so those run from 1850 to 2150, which is a little short for getting a good match on the climate sensitivity. Also, they're using realistic forcing RCP 8.5 rather than 1% and quadrupling, which is a slightly different method. But yeah, I mean, you should be able to make the same kind of relationship and then think about whether the mixed layer depth differences are explainable in that high-res set as well.
I think they did a 1% CO2.
Do they also do a 1%? I haven't seen those things.
Yeah, thank you, Bela.
Yeah, thanks.
Got his hand up.
So Bela, does the two-layer model assume that the percentage of heat that gets into the deep ocean is constant in time?
The coefficient of transfer between the shallow and the deep and the efficacy for the upper layer to atmosphere exchange are both constant throughout the whole simulation. By assumption, I know people have made more sophisticated models than that, particularly looking at paleoclimate simulations. They can't seem to make good sensitivity metrics that go over really big changes. But yeah, that's the assumption in the particular variant of the two-layer model we use. So you have just a short time scale for the upper warming and a long time scale for the total depth warming.
So do you think that's a good assumption? Because there was a group, including several people from NCAR, who thought the slowdown in global warming about a decade ago was because more heat was going into the deep ocean over that period than before.
I would say the two-layer model is not a very good predictor of decadal change. So to the extent that those changes are part of the explanation of decadal variability, yeah, the two-layer model is just not a good proxy for that. But there's no reason why we could not be more sophisticated in the diagnostic conceptual model we use, just like the question just a second ago. We could have used one with a time varying one, but we would have just had more parameters, and you get worried about things like over tuning and that sort of stuff. This was just, I mean, in some sense, this is a framework for how to do this that could be expanded on dramatically by changing the format of the diagnostic model and the format of the linear algebra or potentially nonlinear modeling that we do to relate the emergent constraint to the ocean response parameters in whatever diagnostic model you use.
Justin, you still have your hand up. Did you have a clarification or a new question? Looks like not. Let's go to Bill.
Yeah, I got cut off for a while, so apologize if this question's been asked before. But as far as emergent constraints go, this little model's got more physics in it than many already, in my view. And you are also relating things to things like AMOC and the Antarctic intermediate water and North Atlantic deep water and also tropical mixing. So in your constraints and your models, and this, you get some models that clearly give you a lot of spread, which you need on emergent constraints. But can that fit tell you anything, do you think, about the fidelity of those processes of AMOC, given, I forget which parameter it was that did AMOC, and the other one hit the tropics, that's the Hasselman stuff, and then another one for the Antarctic. I'm just wondering how that fit goes, tells you something about the fidelity of those processes in the models and the spread of those parameters. Do you follow me?
I do follow you.
Because you got a lot of physics in here, in a way.
We got a lot of physics, and the two-layer model doesn't have a lot of physics. So it doesn't have an AMOC, and it doesn't have a Southern Ocean overturning. It just has a surface layer, a deep layer, and an exchange parameter. And the surface layer doesn't have a Northern Ocean temperature or anything like it. It's just a global temperature for the surface layer and the deep layer. So those parameters in that two-layer model are the only representation of those processes. But what the two-layer model does do is it actually predicts the thermospheric sea level rise and the climate sensitivity pretty well. And so that's a kind of bare minimum piece. This separate connection that I was making between the regional mixed layer depths and then thinking about that being, oh, look, that's the AMOC, we recognize that like this. So that's the overturning the Southern Ocean. We recognize that probably has something to do with Southern Ocean mixed layer depth. Those are mechanistic explanations to try and avoid the problem that we are just having correlations between mixed layer depths and those model parameters without a physical mechanism that underpins them. So if I saw a strong correlation, I would not know that there was a causal relationship.
Correct.
So we're tracking those processes to explore the causal relationship and strengthen our belief in the validity of the emergent constraint of regional mixed layer depth to those 2-layer model parameters. Without that, I think we are pretty lost. Now, are those mechanisms well represented or poorly represented in the CMIT model? And did we really use the right conceptual model, or could we have improved by using a better conceptual model? All of that is totally like fuel for future stuff. This is just a first cut at that. And I think that we can say that those are not coincidental correlations. There is some causality underpinning these mixed layer depth that makes sense and heads those coefficients in the direction that you would anticipate based on kind of a first order mechanistic understanding, at least for the correlations that are statistically significant. The ones that are insignificant, I don't care to try and dig into that, probably random variability. All right, I'm gonna stop.
I don't see anyone else right now, but we're into the discussion section, so we can have questions about or discussion about any of the talks today.
Yeah, I think we cut off questioning on Matt Harrison's talk. If there are questions left over, there's an opportunity to get those out there. Not hearing any. Okay. We do have a bit of time left on the schedule for open discussion issues. And, you know, as come up a couple times this week, we're trying to get your input as our, you know, as the working group on our development schedule and process over the next months and years as we work towards CSM3. And to maybe as another attempt to prompt that that discussion, let me just give you my understanding of what our what sort of the external pressures are on our development schedule. All the components are undergoing significant change. Maybe not as radical as, well, we're a fairly radical change and completely replacing a component model, but CAM, for example, will be moving to a new dynamical core. They've got almost a doubling in vertical resolution, new physics coming in. So it's also quite a significant change. They would very much like to begin doing coupled runs in the very near future, like over the next 6-month period, as would we. So we need a moderately stable, in the sense of code, system to work with through this initial phase of trying new component models out together to make sure we're not completely going off the rails. So the expectation is that we will be doing this between, starting now, basically through next summer. And the target atmosphere would be CAM-SE at roughly 1 degree resolution. And I think they're up to 70 some levels, pushing the lid up and also adding layers in both the lower atmosphere and stratosphere. During that doesn't mean we have to stop development during that time, but of course we are human limited, and to the extent that we can both support that testing activity and new development, but we don't want to see development get pushed off to the side completely. So we will need to, really, we've heard a lot of great ideas for things to pull into the model towards a full, releasable CESM3, and we like to support as much of that as we can. but we need to think about how we're going to do that in an organized and systematic way. As Bill has brought up, that we don't want to get into a situation where we have a model that is running in a balanced and stable coupled way and tuned to some extent, and then bring in a new parameterization at the last stage, which throws the whole thing out of balance. So we need to think about how we bring things in together and make use our best judgment to understand which things we bring in what order, and bring in things in groups that we expect to interact strongly with one another. So anyway, I don't know, Gökhan, do you want to expand a little bit on the schedule issue and
yeah, I mean,
offer any other thoughts on how we should proceed as a working group?
Yeah, I mean, you said it, I think, pretty well. As many of you know, we were essentially aiming for some kind of atmospheric dynamical core comparison right about now. And we would be considering spectral element, finite volume, and MPAS dynamical cores. And after some evaluation, we would essentially choose one dynamical core for what I call, or many of us call, workhorse, sort of 1 degree resolution model. It doesn't mean that if the other dynamical cores will be, I mean, all of them will be within the CSM framework. But after reaching out to dynamical core stakeholders and receiving their input and suggestions, after extensive discussions with the atmospheric model working group, and also discussions at the CESM SSC, a decision sort of, we are changing course a little bit. The recommendation was to try to go with the spectral element dynamical core rather than performing yet another evaluation. And many people did not have the appetite to do that, particularly the stakeholders. So we are trying to get an early sense of how the climate is going to look like with the spectral element dynamical core with increased number of vertical levels and higher top, coupled to the new MOM model, MOM6. And it is not, I mean, as Frank indicated, it's not anything final. It's just we are trying to assess with a very short, well, I mean, order maybe century integration, try to get a sense of what we get with no tuning necessarily or anything like that. So that we are trying to have an early assessment of if the SE dynamical core with increased vertical resolution is a viable path to go compared to perhaps MPAS and finite volume dynamical cores. So the timeline that SSC gave is order 6 months to 9 months, essentially, as Frank indicated, from late last year to maybe end of summer. And one of the major impediment for that was, at least we were trying to get the enthalpy sort of figured out in an ad hoc way, at least. And I think, I mean, as you saw Gustavo's presentation, ad hoc implementation is okay. At least we will preserve energy, let's say. And then another natural timeline that came out of from the working group updates from at the CSM co-chairs meetings was that pretty much all the model development groups indicated that they would be at a reasonable spot to essentially consider perhaps an intermediate release of CESM 3 or 2 point something by summer of 2023. So that's sort of the timeline in my head that I have. But it doesn't mean that we are, I mean, after this summer, everybody will do their own stuff. I mean, the intention is essentially every so often to try to bring the component models together as the developments are also going in parallel individually, so that we will have a sense of the coupled system state and try to address issues as early as they arise. So that's all I'll say, I guess. If people have any questions, happy to answer.
Yeah. Bill?
So go Ken. But this time frame you have for this coupling, would that be a deadline to have the workhorse grids figured out, the vertical coordinate as well as the horizontal, which seem to go together? So I can ask that because I don't care. I just would not want to have them changing out from underneath me necessarily.
Right. I mean, for this summer 2023, that is the intention, but not for the immediate evaluation of the SE die core. I mean, for that one, the idea is to go with whatever a workable MOM6 version is so that we can get a quick idea, but definitely for the summer 2023.
But which vertical coordinate? Frank was working on that and we really hammered it down.
Right.
I think it would be worthwhile to hammer some things down.
Right. Frank has some ideas actually.
Well, yeah, I mean, I think, you know, we've got two alternatives that we're pretty happy with, you know, which each have advantages and disadvantages and biases. And I would prefer not to make a decision between those two until we've run both within a coupled framework. So I think over the next couple months, our highest priority will be to run our 75-ish layer level hybrid and Z-star in coupled mode and assess their performance in that system. So I'm hoping, my thought is basically to settle on our workhorse grid in the next 6-ish months in this initial series of coupled simulations, and then choose one of those and have that then be our baseline for development going forward. Is that sensible? People like to comment on that?
That's sensible to me, and it is not even a bad idea if it's not the same as the way GFDL is going, because we don't want to be overly parallel, especially on the vertical grid. But if we both decide the same, we both decide the same. But
well,
it would be that gives us lots of time by this to get this done and then make a decision. So that sounds good to me.
Yeah, I mean, the other element of this initial phase of the evaluation is, I think in contrast to the CESM2 development, we want to be testing biogeochemistry early and making a judgment about the impacts of these choices on the representation of the carbon cycle. That was put off till very late in the development cycle under CESM2, and we kind of got stuck with some biases that were undesirable. So, Steve, you had a hand up?
Yeah, so related to uncoupled development of CESM MOM6, I was really impressed by Matt Harrison's talk and the sensitivities that he showed, and it's quite different from the standard GComp set configuration we use for ocean ice tuning. So I think we might want to consider adopting that approach and you know, putting our ocean model through its paces with a more realistic hydrological cycle.
That'd be great. Yeah, I'm looking forward to seeing Matt's paper. If maybe he could share a preprint with the working group if it's still in review. If you'd be willing to do that, that would be really wonderful. Marcus.
Yeah, thank you. I have a general question. So I haven't met any of you guys in a while. So I left 10 years ago and there were some major biases like the oxygen bias, the precipitation bias, Gulf Stream separation. And I was hoping somehow this would go away in 10 years. But are there any targeted efforts to get rid of these biases, or maybe they are resolved and I haven't seen it yet? Or I mean, especially when you start working with biogeochemistry, the oxygen problem is really it's a hassle.
Yeah. Well, that's why I was indicating we really want. We're starting with a completely new ocean model, so it's not clear. And you know, we've seen this in the physical model development up to this point, that not all biases translate, even though we're running at similar resolutions. There are new ones that emerge and old ones that went away. Gulf Stream separation is not one that goes away easily. So our 1 degree models still don't have a great looking Gulf Stream. Things that Scott Bachman was showing on Tuesday were promising, but those were at 1/4 degree. So yeah, I mean, we're always working on reducing bias. We're also working on improving the fidelity of the physical representation of processes, and that the latter doesn't always lead to bias reduction. It can lead to bias increase, and depending on how compensating errors work out. So it's this as we start this new tuning exercise going into CESM 3, that was an order 2-year process of, as I was describing it the other day, a walk through parameter space, and it turned out to be more of a marathon through parameter space, but that's certainly our target, is to reduce biases.
Okay.
Peter?
So Frank, I thought at one point yesterday you asked whether the horizontal grid that we've been using is fine for the workhorse grid, and I'm not sure we ever got an answer to that. In my opinion, I think it looks fine. So I would think we could go with that one we've been using for the last several months. When I listened to or watched the talks yesterday, there were 2 that I thought were very good. One was is it like an efficiency improvement, which was the statistical model of the wave watch. That really seemed to me to work virtually as well as the full model and was very, very much cheaper. The other talk where I saw made really quite large changes to the ocean circulation that we got was Bill Large's. So it would seem to me that that would be an interesting one to pursue.
Well, we're certainly pursuing those sort of in combination, although Bill or Alper or someone else can comment on how closely the theory model can accommodate the additional information that's required from the wave model for the new wave interaction problem. Yeah, I mean, we have a constituency that is anxious to move on in resolution into eddy permitting regimes, and we have a active CPT project looking at closures for that regime. So there is certainly a constituency for work in that area. We also get a lot of pushback on the cost increase in the model. I resist that to an extent because the cost of CAM has gone up by an order of magnitude since CCSM 4. The cost of the ocean model has not gone up much in the last decade. So I think we're just catching up a little bit. But anyway, certainly I think for the kind of the full suite of problems that we need to be able to address with this model, we need a model, in this resolution regime to accommodate things like large ensembles with biogeochemistry and some of the longer paleoclimate applications, if not an even cheaper version. So there's a bunch of hands have gone up. Gokhan?
Yeah, I mean, Peter mentioned it. I was going to bring up the wave watch model. And I guess we need to decide on what version of the wave watch model we will really need and at what resolution, right? Because if we use the wave watch at the ocean model resolution, and apparently the cost is apparently equivalent to MOM6. So that might be, I mean, I don't know, it's all subjective, of course, but to me, that seems like a rather high cost, but if it is needed, so be it. But we need to probably decide and discuss that.
That's what I was going to comment on, Frank, was so as long as we are only doing the Langmuir mixing within the boundary layer and potentially entrainment, I think Peter's right. There's no reason that we need anything more than the statistical model. But CC Bits's group and Chris Horvat and I are actively working on better coupling between the waves and sea ice. That's where we think at the moment, we do not know how to do that unless they're on the same grid. So we are building prototype versions with matched grids, sea ice, ocean, waves all together, and starting to learn how expensive those are, which is the answer. More expensive. I think WaveWatch is actually more expensive than MOM6 under that configuration. But there's value there, and it does seem to change like the Arctic ice loss pretty substantially, and the scale and sensitivity of the marginal ice zone. So like you're buying climate information for the extra cost, but that's why Paul's presentation was meant. We're trying to get a little more flexible about how the statistical WaveWatch is called, so that the statistical theory waves is called so it looks like WaveWatch, so that the user can switch between those pretty easily, as opposed to being too worried about which one is scientifically supported. Either one being the scientifically supported release, we'll have the other one going as an easy alternative on a variety of different grids in this new approach is the plan. So, but we would really appreciate hearing from anybody in the group about what the priorities are for which kinds of waves and what resolutions and whatever are important, so that we make sure we're not missing something the way that we're setting it up, which is, this is development work being done not at NCAR, or largely not at NCAR. So, we're in the dark as to what the potential other outreach pieces are.
Yeah, go ahead, Bill.
Yeah. So I think Baylor's hit it right on. You would like to have these different wave models be plug compatible. So the first thing to do is come up with an exchange list of variables that have to go in. Even if you set some to 0 in some models, at least all the plumbing that was discussed yesterday for someone to come in and do that is available. And we put that up at the last working group meeting. I didn't get any response to using the wave model for RC transfer coefficient stuff, thank goodness. But the other one, I think we probably could. So the other question, Baylor, that was out there was these reducing the azimuthal and frequency resolution of WaveWatch might save some money. Is anything happening on that?
Yeah, so maybe the GFDL folks, Brandon's not on, is he? No. They're developing other grids of WaveWatch to use in other configurations, and some of them have, basically the later versions of WaveWatch allow you to break out of lat long as you like. And so you can resolve the entire Arctic without having any polar coordinate singularity issues. I believe that version is sort of functional now, but it's that's part of the, transferring that into the CESM framework and when a new grid and all of those pieces and getting that all together is part of what the design flexibility is supposed to be. As far as the diagnostics, we're presently doing all the diagnostics that we would like to have for the Langmuir mixing part, plus all of the cow clip diagnostics, which is just kind of standard like mean wave direction kind of things. Those are the pieces we're building into the wave diagnostics and the wave exchanges. But right now, the theory waves, in doing theory waves for Langmuir mixing, we got really lucky because it doesn't depend on a high frequency dependent phenomenon. So it really is driven by the wind driven part of the wave spectrum. And that's relatively easy to predict. If we were to try and predict, say, depth integrated Stokes drift rather than surface Stokes drift, we would not have been able to do a very good job. And so we want to be transparent about that and show that actually some of those other variables about waves we're actually doing a poor job on by opening up that diagnostics list and doing a better comparison to WaveWatch across all of the different diagnostics.
getting a little bit into the weeds, but maybe I just ask Alper, who's on, if you could just responding to Baylor. I think Alper, so we've dedicated a fraction of Alper's time that is supported on working group resources to wave model support. So we actually have someone now dedicated to being the wave czar in our group, and he has worked on bringing the latest versions of WaveWatch into the CESM code base. So Alper, could you just briefly tell folks where we are in terms of versions and what you think might be necessary to bring the theory wave model in parallel in a sort of a cut and paste kind of way?
Sure. So last year we brought in WaveWatch 3 version 6.14 to experiment with this new surface bands coupling that Brandon and we have been trying to make work. And then this year, actually, like within this month, Mariana has been working on bringing in actually the latest WaveWatch 3, that's 7 point something. So the purpose here is to actually unify our WaveWatch 3 code base with the EMC code base in a way that we could keep in sync with EMC and always get the latest WaveWatch 3 code. So that version of the code is now within an experimental CESM sandbox. We've been running it, and so all the infrastructure is there. And as for the theory waves, I think all we need to do is to just develop a NUAPC cap. I don't know if it has been done yet, but that's pretty much the only task I can think of that would take some time.
Yeah, so Paul has been running it in a NUAPC with a NUAPC cap. So it's just all it is it's like 10 equations that produce things for NUAPC. So it's very simple. The bigger problem, meeting up to what Brandon has proposed, is we actually don't predict those wave statistics. So we need to do the science side of like figuring out what the formula is for those wave statistics, but that shouldn't be terribly hard. We would be able to mimic other WaveWatch implementations very easily. That's our target. And then, as I said before, depending on the problem we choose, we might get lucky and it's easy, or it might not be easy. So the quality will be variable, but the process is straightforward.
Yeah. So
well, I think. Go ahead, Alper.
So I'll just comment a couple of things. Speaking of the efficiency of WaveWatch 3, my experience has been it was on par with MOM6 with the 0.66 degree grid, but the issue is it's not scalable. So with MOM6 we can get like 25 model years per day, but WaveWatch 3 you can't go beyond certain number of cores, so that drops our throughput to about 7 models per year. Another issue with the MOM6 grid within WaveWatch 3 is that it's tripolar, and WaveWatch 3 doesn't support tripolar grid as far as I know as of yet. So perhaps that's another motivation to explore different grids for WaveWatch 3.
Maybe just to wrap this up, is to point Paul here. You've now met Alper, so he, I think, is your point of contact if you want to try running theory wave. Alper had on his plan to run some control cases with this came up in Bill's presentation, run some control cases with legacy Langmuir and MOM6, and maybe as a in parallel with that, we could do that with WaveWatch 3 and theory wave and see how that works out. Keith, you had a comment?
Yeah, this is related to that. It wasn't clear to me from Paul's presentation, does the theory wave have memory? And if not, could that be incorporated into the data wave model? And then we've already got the NUAPC cap. It's just adding some science to that existing component.
by memory, do you mean that it requires
Like,
a restart?
does it
valve?
need to know? Is it evolving any equations in time where it needs to keep state from one time level to a next, or is it just getting inputs and generating outputs?
It's purely diagnostic right now. Which limits the science we can do with it. If we wanted like non-local wave effects and things like that, we would have to put in more physics, but we've been sticking to purely diagnostic because it works just fine for Langmuir.
Yeah.
As we got to more sophisticated applications, we would hit the wall.
So if we keep with that, then there might be some benefit of utilizing the infrastructure that's already present with data wave.
Yeah, Paul, do you have a comment on that?
No, I don't. I haven't looked at data wave at all. So,
okay, Marcus, you're muted, Marcus. Whoop, did we lose him? We lost Marcus.
Marcus, you were muted. We didn't hear you at all.
I think he dropped off.
So
Oh,
my
there
question
he
is not about waves at all. So since you guys are on a wave discussion, please go ahead.
Okay.
Well, we're well past our adjournment time, so maybe we can shift off the wave discussion, and a subgroup of us that are following that topic can meet at another time. But go ahead, Marcus. Why don't you?
Yeah, I'm just in general curiosity. In Europe, here we have several efforts underway now for what they call storm resolving coupled models on a 3 to 4 kilometer scale, ocean and atmosphere. There isn't much like this in the US going on, right? Or at least NCAR is not participating. Is there a reason that would be good to know?
That's not totally accurate. We're maybe a little bit behind, but there are two separate efforts targeting that resolution regime. One called Earthworks, led by Dave Randall, which is targeted at the CESM framework, but this would be using the MPAS atmosphere and ocean as their component models, not unstructured grid models. And then I'm not sure what what's Christiane's project called, which is using CAM-SE and not a 3 kilometer ocean model. I think they would be running with our 10th degree ocean model, but order 3-5 kilometer atmosphere. And that, I think, that one is certainly technically much closer to being going.
You're trying to collaborate with Department of Energy, E3SM, to bring the non-hydrostatic version of the spectral element dynamical core. But that project hasn't started yet.
Yeah, I'm just not sure whether this is a good idea in general to go down this direction. So I thought maybe you guys have some experience and decided not to go down that road.
Well, I think it's largely being led by outside groups, outside of NCAR, but within the CESM framework.
Okay, thanks.
Bill?
No, I'm out.
Okay. Your hand was still up.
Sorry.
No problem.
I just agree with you getting this wave thing together soon and get it done. And that's all.
Yeah, I think the important thing is to get folks working on the same path out of the same repositories and things. So we're not, constantly trying to sync back up with stuff that's, diverging. Other comments or suggestions about what we should be thinking about between now and the summer workshop? Okay. Let me just, as a final thing, remind people that we do have a MOM6 forum on the CESM bulletin board page. So if you Google CESM forums, you'll find it. And there is now a dedicated MOM6 forum, which includes not just the CESM MOM6, but we're sort of welcoming questions and discussion about MOM6 in general. So some of these discussions hopefully can continue in that. You know, if you have the ideas, the questions about science and applications of MOM6, go there. If you have issues with bugs and actual code issues, those go to GitHub, the MOM6 GitHub page. So there are opportunities for open discussion outside of our working group meetings. Gustavo just put a link to the bulletin board in the chat. With that, give people one last chance for comments, questions. If not, I'll thank everyone for this. It's been a really great meeting. You know, we're in a rapid state of flux in our technology and capabilities, and there's a lot of really exciting science we saw this week that hopefully we'll be bringing into our modeling framework in the next months and year. So I look forward to seeing everybody in June at the annual workshop. Be around the same time. It will probably be virtual, I think, Gökhan. Maybe hybrid, I don't know.
We are looking into hybrid if possible.
Yeah, okay. So anyway, we'll leave it there, and you can go back and watch all of this again on YouTube and binge watch talks late at night. So we'll see everybody later.